My name is Amy Solomon, and I'm a series research scientist in the Polar Observations and Processes team. And it is my pleasure to give the modeling and forecasting presentation on behalf of PSL. And the subject matter experts for this presentation are Lisa Bankston, Juliana Diaz, Cecile Penland, Aaron Wong, and Jeff Whitaker. So PSL's modeling and research, forecasting research uses data collected by PSL-led observational campaigns to evaluate forecast systems and process models. In addition, PSL is investigating key processes in the coupled system. I'll be showing an example of research on the interaction between cloud microphysics and radiation. We also do research on fluxes between state components, processes within the atmospheric boundary layer, and inherently chaotic processes. In addition, PSL is developing physically based numerical weather climate prediction algorithms that improve state estimates, reduces systematic errors, improves probabilistic predictions in the UFS. PSL is also producing experimental forecasts to advance process understanding, benchmark operational forecasts, and support stakeholders. The modeling and forecasting research in PSL is central to the work done in this laboratory. It's what connects the research that you heard about for the 3 different themes, predicting extremes, water resources, and marine resources, with research partnerships, observational capabilities, and field campaigns, all of which contribute to the R2X transitions. But within modeling and forecasting, there are 6 areas in which PSL does research that advances understanding to improve NOAA forecasts. They are algorithm development, process studies, data assimilation, post-processing, model evaluation, and experimental forecasts. So in terms of advances in algorithm development, there are a number of teams within PSL that have been developing stochastic physics using rigorous theoretical underpinnings that lead to better ensemble mean forecasts and model variability. And in all of these overview slides that I will be showing, the bullets highlighted in red are the ones that you'll be seeing more detail on in subsequent slides. But I want to highlight that all of the bullets on these overview slides indicate research activities that have had significant advances over the past 5 years. So PSL has been implementing widely used stochastic physics schemes into the UFS and GEFS. In addition, PSL has developed a process-level stochastic deep convection organization scheme using cellular automata. In addition, PSL is developing a consistent uncertainty representation and stochastic perturbations across model component interfaces. So implementing stochastic parameterizations in GFS subseasonal forecasts leads to both a reduction in the root mean square error of the ensemble mean forecast, and it increases the ensemble spread. And that's what's shown in these figures on the right. This is from simulations that include parameterizations for stochastic physics, where the unparameterized physics is represented as a random perturbation to the parameterized physics. And the upper figures are for the 500 millibar omega fields, and the lower figures are for the 200 millibar vorticity fields. The left shows the impact on the root mean square error, and the right shows the impact on the ensemble spread. And if you look at the upper figures first, this shows that including the stochastic physics reduces the root mean square error and increases the ensemble spread, primarily in the tropics. So this means that we're producing more accurate forecasts by reducing the error, but also more reliable probabilistic forecasts by increasing the spread. And the lower figures show that the spatial structure is a function of the physics, because the unparameterized physics is now a function of the parameterized physics. So in addition to reducing the root mean square error and increasing the ensemble spread, including stochastic physics also enhances the variability, and that's what's shown in these figures. So these are the classic Wheeler and Colladis diagrams, frequency wave number spectrum, in this case for precipitation power. The left figure is from TRMS, so these are the observations. The middle figure is for the coupled UFS benchmark 4, and the right figure is for the coupled UFS with 3 stochastic parameterizations included in the simulation. And the first thing you can see in this figure on the right is that the power is increased throughout the frequency wave number space. But if you look at the Kelvin wave distribution, these lines here, you can see that the power is increased in the Kelvin wave distributions, which is indicating that including the stochastic physics is creating a more realistic coupling between convection and the large-scale organization of the waves. So PSL is also improving the physical parameterizations ranging from surface fluxes to cloud microphysics. For example, PSL has implemented new stratospheric ozone and water vapor parameterizations in the GFS. PSL has developed surface flux schemes from stably stratified boundary layers all the way to high wind regimes. There's been an integration of the National Water Model with water agency models to improve simulations of reservoir outflows. A new radiation scheme has been developed that has more accurate representation of the interactions between radiation and cloud microphysics. The Thomson microphysical scheme has been optimized for use in the UFS. And there has been updates in deep convection representation, including a parameterization for convective subgrid organization and a prognostic closure for representation of cloud life cycles. So this is just an example of the developments in physical parameterizations. It's a new radiation scheme developed by Pincus et al. And so what these figures are showing, the upper left figure is showing the shortwave flux at the top of the atmosphere. The lower left figure is showing the shortwave flux at the surface. The upper right is showing the long wave flux at the top of the atmosphere, and the lower right is showing the long wave flux at the surface. And so the blue is showing the existing scheme, which is RRTMG, or the Rapid Radiative Transfer Model optimized for climate models. And the green is showing the improved radiation scheme. And the improvement is due to these updated K distributions in the spectroscopy, which is causing there to be more accurate representation of the interactions between radiation and cloud microphysics. And so if you look at the short wave fluxes first, you can see the significant improvement both at the top of the atmosphere and the surface. And in all of these figures, what I'm showing here is error in watts per meter squared. And on the right, this is showing the long wave flux at the top of the atmosphere in the upper figure, and at the surface in the lower figure. You can see the improvement is more modest, but there's definitely significant improvement with this, this new radiation scheme. And so this is research that has been done under the UFS R2O physics subproject in collaboration with EMC, GSL, and DTC. And it is slated for being included in the operational GFS V17. So advances in process studies. PSL uses a hierarchy of model systems to advance the process understanding of the climate system. And there are 2 points I'd like to make about these research activities. The first is that the majority of these research activities are looking at the interactions between different components of the climate system. For example, how tropical forecast air impacts mid-latitude convection, how ocean and atmosphere coupling impacts organized tropical convection, how land and atmosphere coupling impacts seasonal soil moisture variability and drought predictability, how the interactions between cloud liquid water and cloud liquid ice impact the ability to maintain Arctic mixed phase clouds, and how convection and waves are coupled in the equator. And the second point is that the majority of this research focuses on relatively fast processes such as cloud physics. And that's because the working hypothesis is that the biases on the longer timescales, for example, forecasts on the S2S timescales, in part are due to biases in the representation of the fast processes. So this is showing process-based studies of moist tropical wave mechanisms and prediction. If you look at the figure in the upper right, this is showing the coherence between precipitation and 800 millibar divergence. And the left figure is from ERA interim, it's the observations. This is again the Wheeler and Colodis frequency wave number diagrams. And the right figure is showing the same for the UFS. And what you can immediately see is there's way too much coherence between the large scale and the low frequency variability in the Kelvin wave distribution. And so that's what motivated the investigation of the role of moisture in regulating precipitation in different tropical wave types. And so the lower figures show observed precipitation for 4 different wave types, the MJO, the Rossby waves, the mixed Rossby gravity waves, and the Kelvin waves. And the lower row is showing the precipitation implied by moisture for all 4 of these wave types. And what this is showing is that for the MJO and the Rossby wave, precipitation is primarily due to moisture, while with the mixed Rossby gravity waves and the Kelvin waves, precipitation is due to both temperature and moisture variability. And this is getting at the processes so that we can do more meaningful evaluation of the forecast systems. So this is showing the process studies to improve the representation of Arctic mixed phase clouds and forecast systems. If you look at the upper left, these are observations from Barrow, Alaska, where the y-axis shows surface net long wave radiation in watts per meter squared, and the x-axis shows low level stability in kelvins. And what you see immediately is there are 2 modes. There's a clear sky mode with high, low-level stratification, and also large outgoing long wave radiation. And then there's a cloudy mode, which has very small surface net long wave radiation because the incoming and outgoing radiation cancel, but also very small, low-level stratification because the cloud-driven turbulence reduces the stratification in the boundary layer. And the figure to the right shows the same for the GFD-LCM3, and you can immediately see there's only one mode, a clear sky mode. And this is very representative of climate models and forecast systems in general, that they cannot maintain liquid and clouds at very cold temperatures. And so PSL has done a number of process studies to try to understand what are the processes that need to be included to be able to model these mixed phase clouds. And that's what's shown on the right. These are results from 3 different studies to look at these processes. For example, how you need to include prognostic CCN, which is cloud condensation nuclei. Those are the aerosols that form liquid in clouds. The lower figures are showing the relative impact of the cloud condensation nuclei relative to the ice nucleating particles, or INP. And the upper right is showing a study which looked at the recycling of ice nucleating particles. And that's what I'll talk about in more detail. So what this study found is that in order to maintain the balance between liquid and ice and clouds, you need to allow the recycling of ice nucleating particles, which are the aerosols that form ice particles in clouds. So without recycling, ice particles fall from the cloud system and are lost. But with recycling, as the ice particles sublimate below the cloud, they're allowed to be mixed back into the cloud system. And what they do is it allows the ice and the liquid to be maintained. And so what's seen in this figure is that the solid lines are with recycling, the dashed lines are without. The black shows the liquid in the clouds, the red is showing the ice in the clouds. And what this shows is when the ice particles fall out of the cloud, the liquid increases. And when the ice is allowed to be recycled, you get this, you can maintain the balance between liquid and ice in these Arctic clouds. So this is just some of the results that we've had to try to understand the processes that maintained mixed phase clouds in the Arctic. So advances in model evaluation, PSL has been developing new process-oriented diagnostic tools to evaluate forecast systems. For example, tropical variability in numerical weather prediction, precipitation forecast evaluation in areas of high observational uncertainty, and diagnostic toolkits to diagnose UFS Arctic and tropical system biases. So this is just an example of some of the diagnostics that are developed in PSL to do more process-oriented diagnostics. It's tropical moisture precipitation coupling. And what's shown in these figures, if you look at the figure on the left first, the x-axis shows column saturation fraction. The y-axis shows precipitation rate. The colors show positive precipitation tendency fraction. And the arrows are showing the evolution in time. And these are for 12-hour averages. So for the observations, you can see that if you start with very low column saturation fraction and very low precipitation rate, this is representative of shallow cloud systems, that evolves into higher column saturation fraction and higher precipitation rate, which is representative of convective systems, which then evolves into higher column saturation fraction and lower precipitation rate, which is representative of stratiform systems. And when you go from the shallow systems to the convective systems, there's a moistening. And when you go from the convective systems to the stratiform systems, there's a drying. So when you look at the figure on the right, this is for the GFS V15, you see the opposite relationship. You can see the system starts from the convective system and evolves into a shallow system and with a net drying. And then you go from a shallow system to a stratiform system with a net moistening. And so this is just an example of some of the diagnostics which give us a more process understanding of the biases in the forecast systems. So PSL is also evaluating model biases and processes with PSL-led campaign data. For example, hydrologic and atmospheric model forecasts for high impact flood events, for national water model stream flow precipitation forecasts, for improving the HRRR and the RAP during the Wind Forecast Improvement Project 2, for evaluating HRRR and RAP forecasts using PSL atmospheric river observatories, for evaluating subseasonal coupled forecasts of the Central Arctic over a full annual cycle, and for evaluating the GFS V16 next generation suite against atomic and Eureka observations. So PSL has been involved in a number of observational campaigns. This is just an example from one. PSL has also been involved with the ENRR campaign and the Atomic campaign, but this slide is for the MOSAIC campaign, which is the multidisciplinary drifting observatory for the study of Arctic climate. And this is the first Arctic campaign to observe the coupled ocean ice atmosphere ecosystem in the Central Arctic over a full annual cycle. And what's really interesting about this campaign, and very unique to PSL, is that the models were used to design the observational campaign. And I'll just mention two aspects of that. The campaign was designed as a floating grid box, where within approximately 50-kilometer region, many observations were used to quantify the subgrid variability to be able to evaluate the forecast systems and climate models. Also, the campaign was designed to observe the multi-scale climate system from synoptic to turbulence scales. But what's also very interesting about this campaign is that not only were the models used to design the observational campaign, then the observational campaign, the PSL is leading the international activities to evaluate the forecast system over the MOSAIC year using these observations. And what's also very unique about PSL is that the evaluation for all of these campaigns, from ENRR to Atomic to MOSAIC, was done in real time. So advances in data assimilation. PSL has been improving and implementing new data assimilation schemes. For example, the continued development of sparse input reanalyses in the 20th century reanalysis, and the continued development of the ensemble common filter system to be used in the operational forecast systems. PSL has also been developing and testing a scheme to account for land model uncertainty in UFS ensembles. We've been evaluating land and atmosphere coupling in the UFS to identify targets for land data assimilation, and developing and implementing a state-of-the-art optimal interpolation-based snow data assimilation scheme for the UFS. So there have been a number of advances in ensemble data assimilation research in PSL. On the right here, I'm just showing an example from the 20th century reanalysis. It's for an 1880 Alaska hurricane. And these two figures are showing the impact of adding one observation. And so just to orient you, in the upper figure with the dark purple, that's the Gulf of Alaska. And that's where the hurricane was observed. And the lower figure is showing the impact of adding one observation to the strength of this hurricane in the reanalysis. And so what's really interesting about PSL is that the development of the ensemble common filter in the 20th century reanalysis is what led to the implementation of this in the operational systems, and that was done in 2012. But there have been a number of improvements since. For example, the ensemble common filter is now included in regional model data assimilation. The stochastic physics that I described in previous slides is now used to improve the model uncertainty representation. The scheme has been updated to be for use in the new FB3 DICOR, and parameterizations have been added to lessen analysis shock, such as model space vertical localization to improve radiance assimilation. The filter is also being used to initialize the ensemble reforecast, and is currently being migrated to the JEDI software infrastructure, and which now sets the stage for ensemble-based coupled data assimilation research in PSL. So advances in post-processing. PSL has been pioneering statistical post-processing techniques to correct for forecast errors, such as investigations of the use of artificial intelligence to correct systematic and state-dependent errors in the UFS by prototyping ensemble post-process GEFS forcings for national water model forecasts. And a significant amount of research has been done in developing new methods for statistical post-processing and then applying these methods to many important areas such as precipitation amount, fire weather, snowfall amount, and wind and solar energy production. So this is showing the post-process GEFS forcings for the National Water Model hydrologic forecasts. This post-processing uses a modified ensemble Coppola coupling method, which is high resolution, spatially and temporally consistent, and statistically reliable. It's produced on the NLDAS grid. That's the National Land Data Assimilation System, and then trained with 6 years of data. So if you look at the upper figure in the middle, this is just showing the downscaling of the GEFS precipitation forecast for California. And you can see how coarse these forecasts are relative to the analyzed precipitation on the right. And the lower figure shows the impact of using this post-process technique. And what you can see is doing this post-processing, you can recover the small-scale structure for these precipitation forecasts in California. And on the right, this is showing a significant event that happened on the North Fork River at the North Fork Dam. The blue is showing the GEFS post-process forecast. The yellow is showing the HEFS forecast, so the hydrologic ensemble forecast. The black is showing the USGS observations, and the green is showing the NLDAS2 simulation. So those are the high resolution simulations. And what this is showing is that with this post-processing technique, we can produce skillful forecasts on these smaller scales. So as I said in the overview slide, there's been significant work done on statistical post-processing, and then applications have been done in a number of very important areas. But what this figure is showing is that the statistical post-processing can produce more reliable forecasts than multi-model ensembles. And so in these upper figures, these are the multi-model ensembles. So these figures are showing forecast probability on the x-axis and observed relative frequency on the y-axis. And the upper left is for the raw NCEP ensemble. And what you can see, the red line is showing the forecasts, but more accurate, more reliable forecasts are seen as this red line is moving towards the diagonal. And the Brier skill scores are shown in the box with numbers. So the raw NCEP ensemble has a very low Brier skill score. The middle figure is showing the raw CMC ensemble, which has a much higher Brier skill score. And on the upper right, this is showing when you put the two ensembles together, the NCEP and the CMC, you do not improve the reliability of the forecast. So what the lower figures are showing is that through these different steps with the post-processing, you can produce much more reliable forecasts than you can with these multi-model ensembles. So advances in experimental forecasts, PSL is providing experimental forecasts to benchmark operational forecast systems and provide model guidance to the National Weather Service and CPC. So PSL has been developing the linear inverse model, or LIM, for S2S predictions of tropical SST and OLR, and then using these forecasts to benchmark the operational models. PSL is also developing model analogs for seasonal to interannual precipitation forecasts, developing experimental 0 to 10-day coupled Arctic system forecasts, and doing a number of different forecasts using the GEFS Reforecast V2 datasets. So this is showing some of the LIM work to benchmark operational forecast systems. If you look in the lower left, this is SST anomaly correlation scale at month 6. The upper figure shows the NMME mean skill. The middle figure shows the LIM skill, and the lower figure shows the potential LIM skill. And if you compare the upper figure with the middle figure, you can see the skill in LIM is comparable to the NMME, but also that it doesn't have the systematic biases seen in the tropical Western Pacific, which is seen with the green contours in the upper figure. So this is showing that LIM is a very useful system for benchmarking these operational forecasts that still have these systematic biases. And on the right, this is showing that LIM and the model analogs are currently being transitioned to CPC for operations. So PSL has been producing coupled Arctic system forecasts from 0 to 10 days on a daily basis. And this has been a test bed for improving simulations of ocean, sea ice, atmosphere interactions in the Arctic. And the left figure is showing just a snapshot of the web page where we provide these animations and model output on a daily basis to all the stakeholders. And we're using these forecasts to improve simulations of Arctic extreme events, such as rapid sea ice growth, which is seen in the animation on the right, which is a simulation of rapid ice growth during the 2017 freeze-up season, but also to look at extreme events such as Arctic cyclones, seen in the middle figure, where what we're studying is the coupling between ocean, ice, and atmosphere, and how these processes determine the evolution of these extreme events. And these forecasts are also used to provide model guidance to the National Weather Service, to support observational campaigns, and to inform UFS development. So I've shown that PSL is improving NOAA forecast by developing stochastic physics using rigorous theoretical underpinnings that lead to better ensemble mean forecasts and model variability, by improving physical parameterizations from surface fluxes to cloud microphysics, by using a hierarchy of model systems to advance the process understanding of the climate system, by developing a new process-oriented diagnostic tools to evaluate forecast systems, by evaluating model processes and biases with PSL-led campaign data, by improving and implementing new data simulation schemes, by pioneering statistical post-processing techniques to correct for forecast errors, and by providing experimental forecasts to benchmark operational forecast systems and to provide model guidance to the National Weather Service, CPC, and observational campaigns. So thank you for your attention, and we look forward to discussing this research with you during the panel.